Hello, everyone. I'm Olympia. Thank you for being here with me in this wonderful place called Lights Out Library, and I have a great story to tell you. Tonight, I will take you on a new space cruise to a planet we haven't explored yet, Saturn. We will travel hundreds of millions of miles to immerse ourselves in its vivid rings, its main satellites, and its moons, including the largest of them, Titan. Then we will explore the planet itself. As always, you do not need to watch the video to follow along. If you wish, you may close your eyes and forget about any worries as we embark on this adventure together. We now have a Patreon page for those of you who wish to and can support this project, get more of it, and listen ad-free on your favorite podcast app. Patreon is a platform that allows you to directly contribute to our work financially. If you join, you will get various new things, like the possibility to listen to all episodes with or without background sounds, and regular bonus episodes. We already have 3 episodes available only to our Patreons, with the latest one being The Life of Frida Kahlo, and a new one will be released shortly. You will be able to download all these audios, and you will have your say on the choices of topics, advance releases, and updates on upcoming episodes. We hope to see you there soon so that we may continue developing Lights Out Library, which we enjoy so much. You will find links in the description box and in the first comment pinned under the video. If you fall asleep and wish to resume the video later, or jump directly to a particular part of the story, timestamps are also listed in the description and pinned in the first comment, as well as links to different streaming options like Spotify, Apple Podcast, and Amazon Music, which may be better suited for you. But before we begin, make sure you are in a comfortable position. Take a long, deep, relaxing breath, and when you exhale, release the tension in your shoulders, your neck, release the tension in your facial muscles too, and allow the sound of my voice to guide you through this fascinating journey. Okay, now let's begin. First, what is the distance we need to travel to reach Saturn? As I mentioned during our visit to other planets, the answer is that it depends. The distance depends on where Earth and Saturn are in their respective orbits. If they are positioned on opposite sides of the Sun, this distance is going to be larger compared to when they are aligned on the same side of the Sun. When they are at their closest distance, on the same side of the Sun, the gap between them is about 1.2 billion kilometers. That's 750 million miles, or about 7 astronomical units. An astronomical unit is the distance from Earth to the Sun, a practical unit to benchmark distances in the solar system. This offers an idea of how far Saturn is from the Sun in comparison with our planet. By definition, we are 1 astronomical unit away from the Sun, whereas Saturn lies nearly 10 times more distant, at 9.5 astronomical units, give or take. It's because the orbits are not perfect circles. They are slightly elliptical, shaped like an oval. Therefore, the distance to the Sun varies slightly over time, depending on the position the planets occupy in their orbit. In other terms, our planet, from Saturn's perspective, appears very close to the Sun. When Saturn is on the other side of the star, opposite us, the distance increases, but not dramatically. It expands to 11 astronomical units instead of 7 at its nearest point. If we were to travel at light speed, it would take us around 1 hour to reach Saturn. As we're now leaving Earth's orbit and beginning to accelerate, let's talk a bit about what we'll find when we do reach Saturn. As you probably know, Saturn is a gas giant, the second largest planet in the solar system after Jupiter. Gas planets, unlike rocky planets, do not have a solid surface. They are made of increasingly dense layers of gas. It is believed that at their centers there is a solid rocky or metallic core around which the gas accumulated during their formation process. Gas planets are held together by gravity. The large mass at the core of these planets pulls in and retains the surrounding gas. A hypothesis suggests that these planets must reach a certain size. They cannot be as small as Earth or Mars because a higher mass is necessary to keep them in one place. However, it's possible that both gas and rocky planets have similar origins. They begin as a solid core that appears in the process of star system formation, in orbit around the star. These protoplanets grow by absorbing smaller objects in and around their orbits over millions of years, and may also increase in size by absorbing asteroids that travel the star system. This is thought to be how Earth and other rocky planets like Mars, Venus, and Mercury have formed. However, the orbits of Jupiter and Saturn, which are significantly farther from the Sun than the rocky planets we talked about before, may have had an abundance of hydrogen and to a lesser extent helium that was not absorbed by the Sun. These are the materials that would have been attracted and collected by the two planets, clearing their orbits and forming the various gas layers of these gas giants. I'm using the conditional form here because even though there's a broad consensus about the main aspects of the solar system's formation history, variations exist between the models. These models' theories are inherently difficult to prove. It's not as if we could recreate the experience. For instance, if you examine the solar system in isolation, it might appear as if rocky planets tend to be closer to the central star, as is the case for Mercury, Venus, Earth, and Mars. Further out, you'd find gas giants such as Jupiter and Saturn. And even farther out, ice giants like Uranus and Neptune. However, the examination of other star systems and the growing number of discovered exoplanets indicate that other types of planet placement are feasible. For example, we observe gas giants located nearer to their stars, referred to as hot Jupiters, because of their proximity to their stars. They may have formed far from their star and later shifted orbits, demonstrating that other constellations do not necessarily disprove the theory that gas giants typically form far from stars. This point illustrates that debates about the formation history of star systems and emergence of different kinds of planets remains ongoing. We will elaborate much more on Saturn itself shortly, but for now, let's enjoy the fact that we've considerably reduced the distance to the planet. With each passing moment, it becomes bigger and more imposing. We have surpassed the orbit of Jupiter, which marked the halfway point in our journey. Even though Saturn's mass is substantially less than Jupiter's, the size of the planet and its even larger rings is truly awe-inspiring. Saturn, while less massive than Jupiter by a significant margin, is almost as large in size. It contains 3 times less matter, meaning its mass is 1/3 of Jupiter's, so it is less dense. Why Saturn can maintain nearly the same size with less than 1/3 of Jupiter's mass is an interesting query we will explore later. But before we reach the planet itself and its dramatic rings, let's devote some time to exploring its fascinating moons. The moons of Saturn are equally interesting and could merit their own dedicated discussion. Although they may not be as famous as its rings, Saturn boasts more moons with confirmed orbits than any other planet in the solar system, a total of 146 moons. However, defining what qualifies as a moon raises certain questions. Technically, each block, or even each particle in the rings of Saturn, is a satellite of the planet. With billions and billions of such particles in the rings, we can't really consider them moons because of their small size and lack of independence. The moons I am referring to are distinct bodies, separate from the rings. They have been included in the count of 146 only when they can be repeatedly observed and their orbits identified. If we were to lower the threshold of what qualifies as a moon and accept smaller bodies, the number of moons could potentially number in the hundreds. But for tonight, we're going to pay a visit to some of the most prominent moons. On our list are Titan, which is the largest moon of Saturn and the second largest in the solar system; Rhea, the second largest moon of Saturn; Iapetus, the third largest; and Enceladus. Each of these moons has unique aspects waiting to be revealed. Let's begin by taking a look at Titan, the largest and most famous of these moons of Saturn. It is actually so large for a moon that only one is larger in the solar system, Ganymede, the moon of Jupiter. For comparison, the diameter of Titan is 40% of the diameter of Earth, which makes Titan significantly smaller than our planet. However, it is approximately 50% wider than our moon. For reference, our moon is the 5th largest in terms of diameter in the solar system. The top 2 are Ganymede and Titan, as mentioned. The 3rd and 4th are 2 other moons of Jupiter, Callisto and Io. Coming in at 6th place, Just after the Earth's moon is another Jovian moon, Europa, with Jovian referring to Jupiter. Another element of comparison is that if Titan were not a satellite of Saturn, but orbited the Sun independently, it would be considered another rocky planet, as it is larger than Mercury. However, while it is larger, it is not as massive. Titan has only 40% of the mass of Mercury. Mercury is mostly composed of iron and dense rock, whereas a large portion of Titan consists of ice, which is far less dense than the materials we talked about. Despite its distance from Earth, Titan was discovered fairly early, around the mid-17th century, by a Dutch astronomer, Christian Huygens. This was relatively later in comparison to the moons of Jupiter, which had been discovered a few decades earlier by Galileo. Titan is about twice as far away, yet it is large for a moon and is relatively shiny with a uniform yellowish atmosphere. This characteristic aided Huygens in detecting and studying it, much like the planet Venus. Titan reflects sunlight and is far enough away from Saturn to be differentiated from it with relatively rudimentary telescopes. Yet for 350 years, our knowledge of Titan remained elementary. Their surface was impossible to view, hidden beneath a thick and impenetrable atmosphere, resembling the situation of Venus. Our comprehension of this moon's surface and atmosphere has mainly been formed via discoveries made in the past few decades by probes, particularly in 2004, when the Cassini probe approached it. It is relatively uncommon for a moon to possess a dense atmosphere. This can only occur when the moon's size is large enough for its gravitational pull to retain the atmosphere. As we've noted, Titan is the second largest moon in the solar system. Additionally, over hundreds of millions or even billions of years, these moons must be able to preserve their atmosphere, as an atmosphere can be lost due to a collision with another body, or by passing too closely to a planet that could steal it, or it could be carried away by the solar wind, which is the flow of particles and radiations that come from the sun. These are extreme conditions, and perhaps for this reason, only two moons with a significant atmosphere are known in the system: Titan and Triton, a moon of Neptune. Both of these moons are relatively large and far from the sun, with different conditions that probably explain how they have managed to retain their atmospheres. Other moons generally have very faint atmospheres, not dense enough to be comparable to the kind of atmospheric conditions we are familiar with on Earth. However, Titan truly differs. Its atmosphere is very heavy and dense, so dense, in fact, that the surface pressure is higher than that on Earth. It is estimated to be close to 1.5 atmospheres, slightly higher, 50% higher than the atmospheric pressure we are accustomed to at sea level on Earth. This level of pressure would be like swimming a few feet underwater, an experience that would be perfectly bearable to human beings. While the atmospheric pressure might be livable, other conditions are not. The atmospheric composition is primarily nitrogen, accounting for 97% of it, along with methane and traces of hydrogen. Our own atmosphere is 70% nitrogen, but we also have 20% of oxygen that we can breathe. Titan's atmosphere doesn't have gaseous oxygen on its surface, meaning we couldn't breathe without a suit. Another major problem for human beings would be the temperature. Titan is nearly 10 times as far from the Sun as Earth, and this produces only about 1% of the sunlight we receive. Not much sunlight at all. On top of that, 90% of it is absorbed by Titan's thick atmosphere, with only the remaining 10% reaching the surface. Now, because the atmosphere is thick, there also exists a greenhouse effect like that on Earth, helping to retain a bit of heat. Despite this, the temperature on Titan is frigid, measuring approximately 94 Kelvin, or 179 Celsius, a temperature at which water would instantly freeze. But without this greenhouse effect, it would be even colder. And yet, another problem that man could face on the surface is the constant darkness, with 1% of the light of night on Earth, and the thick atmosphere hiding the sun. You are plunged into near perpetual night. But let's say we have a suit with heating and oxygen mask and lighting. What would we see at the surface of Titan? An extraordinary landscape, actually. At the same time, it's completely alien chemically, but somewhat familiar in its geography. Titan is thought to have standing bodies of liquid on its surface, including rivers and lakes and seas. Except these bodies don't contain water because it would freeze, but rather liquid hydrocarbons like methane or ethane. Titan is believed to be the only place in the solar system, except Earth, to have such liquid bodies with a cycle of evaporation, clouds and rain like on Earth, except it's not water but hydrocarbons. Apart from the cycle of precipitation, mountains and volcanoes have been observed, but these are not Earth-like volcanoes. They are cryovolcanoes. A cryovolcano erupts volatile materials and gases, such as ammonia, water, or hydrocarbons. All these materials that astronomers call ices. It's not just water ice. It is believed that these materials ejected by cryovolcanoes come from underground reservoirs and rise to the surface, a bit like lava on Earth. But these are much colder materials and they are not rock. It has also been observed that the surface of Titan appears relatively young because it doesn't have many impact craters. Partly this is likely due to its atmosphere, which, like ours, eliminates smaller asteroids by disintegration. But it is also because there is geological activity on Titan. It seems that new material is expelled from the inside of the moon, presumably by these cryovolcanoes, in large enough quantities to slowly replace surface materials over a span of several million years. This activity erases traces of impacts and refreshes the surface. One question about Titan was raised when its unique set of conditions and composition became better known. Is there the possibility of organic life on this moon? On the surface, this sounds very unlikely due to the temperature. But like other moons of the solar system, such as Europa, the moon of Jupiter, there could be subsurface oceans under the thick ice sheet. And in these oceans, maybe, the prerequisites for simple organisms or prebiotic conditions could be present. As of today, there is no evidence that Titan harbors any kind of life, and if it does, it would have to be life that relies on other energy sources than sunlight. Like the life forms on Earth that depend on hydrothermal vents near the ocean floors for the energy and nutrients they need. This is theoretically possible. In a strange way, despite its vastly different materials and climate, Titan is considered to be the body in the solar system that is most similar to Earth in geographical terms. However, its surface is constantly plunged into darkness. At this distance from the Sun, even if it could be seen through the atmosphere from the surface, it would only be a very distant and faint light in the sky, not the big shiny ball we are used to. Let's now take a look at the second biggest moon of Saturn, Rhea. Rhea aligns much more closely with our perception of the moon. It's composed of rock and ice and has a scant atmosphere, just a very tenuous layer of gas. It is significantly smaller than our moon and was discovered 20 years after Titan by an Italian astronomer, Cassini. Hence the Cassini-Huygens mission was named in honor of the early discoverers of Saturn's moons. Rhea may not be as remarkable or as original as Titan, but it holds one record. It is the smallest body in the solar system that has been precisely measured to experience hydrostatic equilibrium. But what does that mean? Planets and moons are round to a certain size, while smaller bodies can be irregular. There is no instance of a body the size of Earth, for example, that would be elongated or irregular. But why is that? It is because of hydrostatic equilibrium, a concept from fluid mechanics. Under the solid crust of planets or moons lies a viscous fluid, composed of very hot material, generally rock and metal. Gravitationally, the reciprocal attraction of all this matter keeps it as one single object. The internal gravitational force exerts pressure on the material at the center of the body, and this weight from the outer layers of matter compresses the center. If this gravitational force was not counteracted, the body would collapse on itself. The mass would remain the same, but it would become increasingly smaller because the matter would become more and more compact. This doesn't happen because there is an opposing force that causes materials to expand, a pressure gradient force. The volume of the body stabilizes at the point where these two forces cancel each other out. Large objects in space tend to become spherical because of this equilibrium of forces. The spherical shape ensures that forces are evenly distributed around the center. This, however, only applies to large-scale objects that are not entirely solid. Small or medium-sized asteroids are not affected by this because they aren't viscous. and are not large enough for gravitational forces to compress them or melt their cores. The pressure gradient force and the equilibrium it forms with gravitation are also crucial for the Earth's atmosphere. Without resistance to gravitation, the entire atmosphere could be pulled to the ground and would not be as thick as it is. On the other hand, without gravitation, the Earth's atmosphere would expand around the planet and diffuse into outer space. Our atmosphere maintains its current state because of this hydrostatic equilibrium. You may recall when I mentioned earlier that Saturn is almost as voluminous as Jupiter, but only possesses a third of its mass. How's that possible? This occurs because the mass and the size of the body do not always coincide. It may seem logical that if you make a planet heavier by adding more material, it will become larger. However, this is not always the case. The size of a planet could decrease even if you add more material, because this addition affects its hydrostatic equilibrium due to an increase in gravitational force. In this respect, Rhea is remarkable because it is the smallest known body in the solar system currently under the influence of this hydrostatic equilibrium. As a result, Rhea has a spherical shape. Had Rhea been just a touch less massive, it would likely have adopted an irregular shape. Let's now explore another moon discovered by Cassini, Iapetus, named after a Titan from Greek mythology. Like various other moons of Saturn, Iapetus is similar in size and estimated composition to Rhea, mainly ice with a lesser amount of rock. At first glance, Iapetus appears spherical, but it is not. It falls just below the hydrostatic equilibrium threshold. As a unique feature of this moon, its poles are squashed, and it has a long and high ridge or mountain chain across the equator, giving it an appearance similar to a walnut. Given the size of the moon, this mountain chain is impressively high, reaching up to 20 kilometers. That's almost 12.5 miles. This is more than twice the height of Mount Everest, on a moon much smaller than Earth. For comparison, Iapetus has roughly the same surface area as Australia. There's no clear explanation for how this ridge formed, but several hypotheses have been suggested, including the collapse of a ring system, ejection of icy material from inside the moon, or it might be a remnant from its formation stages as evidenced by its ancient impact craters. Another mystery about Iapetus is its unusual coloration. One hemisphere is dark and the other very bright, a stark contrast that has puzzled astronomers ever since the moon was observed up close. There are several theories, including one that suggests falling material on one of its sides from another smaller moon of Jupiter, Phoebe, is responsible for the distinguished difference in color. Before we continue our journey, let's take a look at one more moon, one with a truly unique feature, Enceladus. Enceladus is small, not large enough to be spherical, and has an ellipsoid shape. In other words, it is shaped like a sphere compressed on both sides. If you put a ball in a press and flatten it, you get an ellipsoid. Due to its small size, it was hard to see from Earth and was discovered in May 1789 by a German astronomer, Herschel, over a century after Titan and Rhea. Nonetheless, Enceladus is one of the most reflective bodies in the solar system, reflecting light primarily because its surface is covered in ice. The ice remains fresh and clean because a large part of it is renewed by frequent cryoeruptions from cryovolcanoes. Enceladus is thought to host subsurface liquid oceans and is another moon considered to possibly have conditions favorable to biological life. No surface life like on Earth, but life in the depths of dark oceans under its icy crust. So, how can we estimate what these distant moons are made of? Some of them have been approached by probes, but we certainly haven't been there to take samples. These estimates come from several different methods. The first is based on the size and mass of celestial bodies. The size can be observed and the mass can be inferred from their influence on other bodies due to gravity. These calculations are complex and involve many factors and unknowns. However, astronomers and mathematicians have been dealing with these celestial mechanics problems for centuries. By combining size and mass estimates, one can gain an initial idea of what a body might be made of. For instance, if it's very massive or heavy for its size, this suggests it contains heavy materials like metal, or if it's light, it might be composed of ice or lighter rocks. The second method involves spectroscopy, which is the observation and measurement of the spectrum of light. Different elements have unique spectral signatures as they emit at varying electromagnetic wavelengths. So we can determine a lot about the composition of distant bodies by measuring these wavelengths. However, this method isn't foolproof because the signals are often faint, especially for distant bodies, and can become mixed. So they require careful analysis. A third method involves combining all this data with what we know about the chemical composition in their environments and formation models. We know, for example, that heavier elements tend to migrate towards the core of a planet, while lighter elements tend to stay closer to the surface. We also know that certain conditions of pressure and temperature determine matter's state: solid, liquid, gas, or others. I'll discuss metallic hydrogen more when we delve deeper into Saturn's surface. So, with these sources of data and the interpretation we can do with them from the various disciplines that astronomy touches on, such as physics, chemistry, mathematics, optics, and spectroscopy, we can build solid hypotheses about what planets and moons are made of and how they are structured internally, even without having physically traveled there. Still, these are only theories and not certainties. There may be changes in the future, as there were some in the past. But at this point, they are the best informed guesses we can make based on available information. As we continue to approach Saturn, it is now time to talk about its rings. The 4 moons we quickly looked at are farther away from the planet. But as you know, because you have seen pictures of Saturn, the rings start quite far from the planet too. They are gigantic. And actually, they are even bigger than the pictures suggest, because what we see in photos or artist views is just the most visible ones, the densest, the shiniest parts of the rings. In reality, they extend tens of thousands of miles, more than the planet's radius. These rings are also incredibly thin relative to their size. Thickness varies from 1,000 yards, which is less than a kilometer at most, to only 30 feet or 10 meters. This is not even the proportions of a sheet of paper. The rings are incredibly thin. However, we see them very well, or at least the rings that are relatively close to the planet. This is because they are also very shiny and made almost exclusively of ice, with barely any dust, less than 0.1%. The main rings are made of billions upon billions of particles and small objects. The largest ones are only a few meters or yards across, and they are all little satellites that orbit the planet together. This ice is clean enough to reflect sunlight, and this is why we see the rings so well. Another fact that could sound counterintuitive is the minuscule amount of water or matter the rings contain. The total mass of the rings has been estimated, and it is less than the Antarctic ice sheet on Earth. For comparison, we have to imagine the ice sheet of the South Pole from the Earth, spread on a surface and area that is 80 times larger than the total surface of Earth. That's how thin and delicate these rings are. But why are they so big? How and when did they appear? Historically, the dominant hypothesis was that the rings dated from the formation of the planet or close to it. This suggests that they were billions of years old. This hypothesis was not based on very solid measurements or models, and it was increasingly challenged, especially a few years ago when the Cassini spaceship explored the rings. The rings were revealed to be far less massive than once thought, and it was also confirmed that they regularly lost some of their matter that fell to Saturn. This means that these types of rings come with an expiration date. They will get depleted eventually. The problem with the old rings theory is the shine they possess. Over time, they should have collected cosmic dust particles that would have darkened them. But as I've mentioned, they are made of 99.9% pure water ice. So, from these observations, it appeared that the rings could be much younger, perhaps only 10 to 100 million years old, which would be a small portion of Saturn's existence. And based on current observed depletion rates, the rings may disappear in 300 million years. The edge of the rings is something, but it doesn't tell us how they have formed. Here we have two main theories. The old one suggests that the rings are left over from the original nebula material from which Saturn and the whole solar system formed. All these particles would have turned into satellites of Saturn early in its formation process, and so the planet would always, or nearly always, have these rings. As we mentioned earlier, this theory is now rather old-fashioned, because it fails to explain why the rings would be pure ice, and it doesn't take into consideration depletion of the rings into account. Probably because this was not known when the theory was proposed. The second, more recent dominant theory suggests that the matter the rings are made from comes from an old moon of Saturn. The orbit of this moon could have decayed, meaning the moon tended to fall towards its planet instead of maintaining the same direction from it. Once it was close enough, the gravity from the Saturn's large mass, or tidal forces as they are called, would have ripped apart this moon. It would have been shattered over time into all these small pieces that stayed in orbit and formed the rings. A variation of this theory proposes that it was not tidal forces, but a collision between the moon and a comet or a large asteroid that shattered it. This corresponds with the relatively small quantity of matter in the rings. You may remember that these contain less material than Earth's southern ice sheet. However, this theory doesn't reconcile well with the composition of the rings, which is almost purely ice. This is because there is no example of a pure ice moon anywhere in the solar system. Granted that there are floating blocks of water ice, and water is abundant on many moons. However, even the moons with the most water, like Enceladus, which we visited earlier, still contain about 20% rock. So, if a moon was shattered near Saturn, why did its ice stay in orbit while its rock disappeared? This gives rise to another variant of the same origin theory for the rings. Instead of an entire small moon, it might have been just the ice mantle of a larger moon, possibly the size of Titan. Such a moon's orbit would have decayed during the formation period of Saturn. Its ice mantle would have been stripped and remained in orbit, while the rest of the moon would have fallen into Saturn and been absorbed by it. Still, these remain theories, each with their own merits, and nothing is definitively proven. For instance, the brightness of the rings and their purity are cited as evidence that the rings are young, not hundreds of millions of years old. But perhaps the darker material could have settled in certain areas of the rings. They are not uniform. There are divisions between them and zones that appear more or less bright. Perhaps clumps form within the rings with impurities, and then they get disrupted by impacts, effectively cleaning up the rings. We can't be certain. Thus far, the most plausible hypotheses for the presence of all this matter in orbit around the planet remains a shattered moon, either wholly or in part. The biggest dilemma is discerning when and how this happened. You're likely familiar with the ring's appearance and how they resemble distinct stripe-like subdivisions. There are lines that are more or less bright and sometimes feature entirely dark spaces in between them. These subdivisions have been named based on their appearance and distance from Saturn. A commonly used categorization begins with ring D, the one closest to Saturn, which is quite faint and was confirmed only in 1979 by the Pioneer 11 probe. Proceeding outward, there are rings C, B, and A, each with divisions between them. The nomenclature becomes less intuitive when moving further away from the planet. The ring after A is named F, followed by E. Each of these different divisions has unique physical characteristics like thickness and particle density that make them either more or less bright. Let's continue our approach towards the imposing mass of Saturn. Despite appearing almost as big as Jupiter, Saturn has less than 1/3 of Jupiter's mass. This discrepancy comes from the unique equilibrium of mass and size we discussed earlier. Jupiter, being more massive, is also more compressed, hence significantly denser than Saturn. When comparing chemical compositions and structures, if we leave aside the density difference, the two planets share many similarities. Both are gas giants believed to have a metallic and rocky core, surrounded by enormous layers of gas held together by gravity. The term gas is used here because hydrogen and helium, the main constituents, reflect the nebulous composition from which the solar system originated. Primarily hydrogen, followed by helium, the two simplest elements were most abundant. The so-called trace elements were present in tiny proportions. But Saturn is not like a mere cloud. Its density is far greater. The planet has a core believed to be surrounded by a layer of metallic hydrogen. Hydrogen that is so compressed that it transcends a liquid state. This unique state is called metallic, due to its ability to conduct electricity. A topic we previously covered during our space cruise to Jupiter and its moons. Above this layer of metallic hydrogen exist zones of liquid hydrogen and liquid helium. It's only above these that a genuinely gaseous outer layer begins. Consequently, parts of Saturn are denser than anything you'll find on Earth. Although Saturn has 95 times the Earth's mass, for comparison, Jupiter has over 300 times. When averaged out with these less dense outer gas layers, Saturn's average density is lower than water, about 30% less dense. In its entirety, it could be deemed a relatively light planet. However, Saturn isn't solely composed of hydrogen and helium. Its core, as mentioned, is believed to be metallic and rocky, with traces of other elements present. These other elements contribute to the planet's yellowish hue, generated by crystals of ammonia in its upper atmosphere. Saturn's surface appears more uniform and less feature-ridden than Jupiter's, with a hint of more yellow around the equator. It might be hard to discern in pictures, but its shape isn't strictly spherical. This is due to its rotation and its relatively low density. The rotation creates a centrifugal force, and this flattens the planet a little bit. It becomes an ellipsoid, like Enceladus, the moon we visited before. Except contrary to Enceladus, Saturn is not a body with a solid surface. It is a rotational ellipsoid. It takes this ellipsoid shape due to its rotation. If the rotation stopped, which is not going to happen, but let's say it would theoretically, then the centrifugal force would dissipate, and the planet would become a sphere. Due to this hydrostatic equilibrium that we talked about before, that would no longer be held altered by the rotation. Much like other gas planets, Saturn doesn't have a distinct surface. Upon diving into it, one would gradually encounter increasing gas density, which after hundreds of miles of travel towards the planet's core becomes dense enough to transition from gas into a liquid state and subsequently metallic. At the core, there is a mass of heavy material, predominantly iron and rock silicates. Saturn's distance from the Sun contributes to the longer time it takes to complete one revolution, referred to as a Saturnian year, almost 30 Earth years. The view of Saturn from Earth changes a little during this long revolution due to the varying angles of perception, at times from above, sometimes from below the rings, made possible because all planets orbit around the Sun and sit on the same plane, albeit inclined slightly differently. Saturn's orbit around the Sun is slightly more elliptical and inclined by just over 2 degrees relative to Earth's orbital plane. Therefore, taking the Earth's orbital plane as a reference, Saturn crosses it twice in 30 years, appearing alternatively from above and then from below. Despite its peaceful surface appearance, Saturn houses some of the solar system's most violent winds, reaching up to 500 meters per second. Only Neptune's winds are known to exceed this speed. For comparison, note that the speed of sound in our atmosphere is 360 meters per second. So, Saturn's winds are surprisingly supersonic. Saturn's southern pole is home to a unique feature, a warm polar vortex, a rotating gas region the size of Earth, around which blows the planet's fastest recorded winds. Heat, believed to emanate from inside the Sun, is ejected from this vortex, despite the average atmospheric temperature of Saturn being measured at minus 185 degrees Celsius, which is minus 301 degrees Fahrenheit. The temperature inside the vortex is approximately minus 122 degrees Celsius, which is 187 Fahrenheit. 60 degrees Celsius or 140 degrees Fahrenheit warmer, but still freezing. These temperature disparities likely explain the violent winds surrounding the vortex. There is much more that could be said about Saturn, with some people dedicating their entire lives to the study of this planet. But for now, it's time to conclude this journey in the solar system and return to Earth. Whether you're ready to drift into sleep or eager for another tale from my library, I hope you've enjoyed our journey. And until we meet again, good night. Sleep well.